Hi everyone, welcome to this lecture 7 of the course Ordinary Differential Equations. So today we are starting chapter 3. Okay, this is the outline of the chapter 3. And so in this chapter, we are considering a two-dimensional ordinary differential equation with A is a matrix, so it's linear. It's a linear differential equation. And as we will see in the chapter, and we will see that in detail, the behavior of this equation relates to the eigenvalues of the matrix A. All right, so I first propose you this exercise. Solve these equations, find the solution of these equations, and then draw a sketch of the trajectories in the x, y plane. So let us give the correction of the exercise. So, so this equation now should be quite straightforward to solve. So solutions of these equations are just exponentials. So for x of t, the solution is x0 exponential minus t, and for y of t, you have y0 exponential 2t, right? And so those, when you choose different initial conditions, x0 and y0, for each x0 and y0, you have a trajectory. And since we deal with linear systems, the solutions are defined, well defined for all times. We proved that on the last, in the lecture 6, because my matrix R defines a Lipschitz function, right? So then, so again, computing this, for each x0 and y0, the solution is quite straightforward. And now we are going to represent it in the xy plane. And so if x0 is non-zero, you can show that y of t is equal this expression of x of t. So it's a rare event. Here we can explicitly compute y as a function of x. So that's perfect for the drawing. And so here is the drawing. Here are some special solutions of my equation. So in red, we draw the solutions corresponding to y0 equals 0. In green, the solutions representing initial conditions with x0 equals 0, but y0 non-zero, right? Because if you have x0 and y0 equals to 0, what you get is this fixed point, the unique fixed point that I put here in yellow, all right? And then in blue are other specific conditions that I draw thanks to the explicit formula y as a function of x. And for example, here I have some x0 positive and some y0 positive. And then as t is going to plus infinity, I follow here in the direction of this arrow. And then as t is going to plus infinity, my x is going to 0 and my y is going towards plus infinity. Yeah, and the trajectory lies in the function defined by y of t as a function of x of t. All right. Okay, and yeah, you have typical solutions in each quarter of the plan. And now my yellow point here is called a saddle node. A saddle, or just a saddle node. This corresponds at one eigenvalue negative and one eigenvalue positive, right? So maybe just keep in mind that we have like special trajectories, right? In red and in green, the fixed point, special trajectories, and then general trajectories. And this will be also the case for different eigenvalues. So next, we will move to another system. All right, so the next exercise is the same, but you change the matrix. And so here you can see the new system. It's a linear system. In this chapter, it's all about linear systems. And try to do the same. Try to find the solutions, explicit, try to compute the solutions, and then draw it in the y-x plane or xy plane. All right, so I'll let you a few minutes to do that. All right, so let's solve this exercise. So here, as we will see, computing the eigenvalues and associated eigenvectors will be crucial to compute the solutions of my linear ODE. So we can use this formula here. You know that the eigenvalues lambda 1, 2 are given by this formula. So here's the determinant, right? And when I apply this formula to this matrix A, so my trace is 0, it's 1 plus minus 1, it's 0. My determinant is -4, because it's -1, -3, -4. And then my lambda 1 is -2, thanks to the formula, and my lambda 2 is 2. Next, we compute the associated eigenvectors. So it's a computation. So I find V1, which is equal to 1 minus 1, and V2, which is equal to 3, 1. And you can see that now here x of t equals alpha for any real alpha. Here I have my eigenvalue, and here I have the associated eigenvector. You can see that this is a specific solution. You can prove that, right? You just take the derivative of that, you find something, and then if you apply a to this x of t, you find the same thing, which means that x of t is a solution, right? Then you do the same thing, so with v1 and v2, and then since everything is linear, the solutions are given by this formula, all right? So this is the answer to question 1. And then you can draw the solutions, all right? So in red, as for the previous exercise, I draw which is called a stable manifold, because if you start there, you're going to the stable point, right? And this is associated to the first eigenvector with the negative eigenvalue. And in green, you have the eigenvector associated to the positive eigenvalue. And this is also a specific solution, which is an unstable manifold, because when you start there, you go away from the fixed point. And then in blue, you have typical trajectories, and they change direction when they cross the null lines, which appear with here the dashed writing, right? And so this gives the whole picture for the trajectories corresponding to a saddle node in the general case. All right. And so here I just show you the computations for the asymptotic behavior, meaning that when t goes to plus infinity, my trajectory will approach the unstable manifold, and when t goes to minus infinity, we will approach the so it's the that's t. And when you go to minus infinity, you will be close, you will be next to the stable manifold, meaning that in the past you started close to the stable manifold, and when t grows, when t goes to infinity, you will approach the unstable manifold. All right. So next you can solve this exercise. So in this case, so the solutions are explicitly given by that. And in order to represent it here, which again, it's a rare event, you can explicitly write y as a function of x if x0 is not 0, right? You have that. So in red, this is the solutions corresponding to x0 equals 0, and this corresponds to the greater eigenvalue in absolute value. And in green, it's the other one, right? And so the two eigenvalues here are negative. And in blue, typical trajectories, and they lie in the manifold y equals a constant times x squared, right? And in yellow, the stationary point. So next, we are doing this exercise. All right, so I'll let you with that.